about is a feasibility study. Like here, the error that we ended up with on this problem was 1.189. So somebody says, no, we have to be within half an inch. 1.189 is no good. I want to be within half an inch of the true height. You guys kind of with me? Is that cool? Maybe. Because of course, if you want to know this within so much, you want to control within so much. You don't want to say, give or take 800 years. I'm going to live another 30 years, give or take 70 years. What good is that? That's bullshit. If you're my doctor, you tell me that. It's like, no, this is not good. You guys come with me? So I want to control how much off I am. So the give or take of that is, if I want to be that close, what's going to have to change?
The number.
Good, the number of people. So this is a feasibility study in the sense that if I need to talk to 800 million women, that's not feasible, right? But if I need another 800, that might be okay. You guys kind of with me? 800, in fact, would be not feasible for me. I wouldn't want to do that. But so let's actually do a little bit of algebra first to see where that formula that's sitting there comes from. So what part of the equation do you think that within 0.5 inches, what part of that equation do you think that relates to? The air. Within is kind of like a plus or minus. You want to be within 3 pounds of something that's give or take 3 pounds, plus or minus. So I want this piece, I want the air to be 0.5. Right? So let's not put this number in yet. Let's do this in general. If the air is this, that's good if I know n. If I don't know n, I want a formula that's solved for n. So this is the very little tiny bit of algebra you actually have to use in this class. How do I solve that equation for n? Don't say, like that. No.
Cross multiply.
Sort of.
And then square it, and then...
Yeah, so I can multiply the root n up. Is that cool?
Yeah.
And divide the e down. So I get root n equals z sigma over e. Is that cool?
And you square the...
How it is so far? Nothing too taxing there, hopefully. You all survived 103 or 110.
Square.
Then square both sides, and then you see where that equation comes from. 11. So n equals that business there. Cool. So now I can do this. Go ahead and try that out. Now it's just another plug and chug thing, but it's good to know where the hell it came from. Figure out how many women you would need to be within half an inch of the true mean height. We're still at 98% confidence, so what's the z-score?
2.33.
We have the same one we had before, 2.33. Right. There's 0.5.
7. 135 plus 72.
135.7. You can't do 0.7 over 1.
Yeah, so everybody get that? 135.7, is that?
136.
Yeah, a good point. Right, that 0.7 woman is a little freaky of an idea. It's a woman or an 8, so you always round up no matter what that number. Because this says you need at least 135.7. So even if it came out to be 135.01, you need at least that much to be within 0.5. So if you want 135, you're screwed. You're outside of it. So you just always round up to be safe, to be more conservative. So we need 136 women. Now, what if I had asked, how many more women do you need to talk to or look at? You've already done how many? 24, you've already measured them, so you take 136 minus 24, 11. So you need
112.
112 more. Which is not horrible, right? That certainly is doable. You already talked to 24 women. It shouldn't be horrible to try to find 112 more, right? How are we doing so far? If that number would have come out to 78,000, that would have been troublesome. A little bit difficult. Okay, maybe. All right, so real quick, just for make sure we all got the idea. Do note part C. There's now one at 90% confidence interval for the same numbers.
So that's basically only the z-score changes?
Exactly. I love it. Just make sure everybody can get that z-score correctly.
You might have to change it.
Oh, yeah.
Are you doing it really?
That's not very helpful. Too bad. No, stop. Too low.
What's the difference between the two? It's the same.
That's why the little stars there. All right. And what that does is just says you split the difference. 1645. So when you see those little stars there, that means you're going to go right in the middle because it's exactly symmetric around it. So you take the number in the middle. You're going to start to remember some of these numbers like 1645, 233, 196.
No.
Yes, you will. If you don't, that just tells me, oh, you're not doing your homework. All right, I see. I understand.
645
Is the z-score, right? Cool. So that's the only difference in the work.
Except on the number, are we using the original number that you gave us or the one that we found?
The original number. Yeah. Now, looking at part A, same stuff from part A. So X bar is still 64.17. Area is 2.5, and is still, what was it, 24? Because if I did take 112 more women, the X bar probably would change, and I didn't tell you what that was. So this is based off of part A. And now you just throw all your stuff in. You got 64.17, give or take. The z-score we got now was 1.645. Calculate that error first.
0.839.
$839.
Yeah.
Take your word for it. Right, then you just add it, subtract it. The math itself is not difficult. It's, of course, the concepts that got us to this equation that were difficult.
So we have to rewrite the equation? The conclusion?
Yeah, every time you do a confidence interval. So it would be exactly the same wording as this, except you say we are 90% confident that the mean, the interval, whatever you get here, would contain the true mean height of women. So why is the error smaller?
We're less confident.
Because we're less confident. So we that's not a really great way to improve the error, right? Our error is better than it was before, but just because we said let's be less confident about it. So now there's a 10% chance I'm wrong because it didn't go out very far. Good. The better way to improve your error and keep your confidence high is to get a larger sample. But sometimes that's not feasible. Okay. All right. So that's section 7.3. Now we're going to do 7.2, which talks about percentages. So, the first thing I need to introduce for this, and to kind of go back and make sure you understand the distinction. What was the symbol mu again?
Population.
Population mean, and what was the X bar?
The sample.
So the symbol P versus Q represents what? Success probability for a population. That was never really stated before fully. But like I said, 11% of Americans are left-handed. That was the entire population I was talking about. So P represents the population percentage of success. Q would represent the population percentage of failures.
Opposite.
You're going to love this. Yeah. The symbol for sample percentage is P hat. Not something you ever want to wear, it sounds like. Get all that out of the way. P hat. I was in there when they came up with this symbol. I don't know what that day was like with these people that were made it up. This is a sample
People must have been pissed off.
percentages of success, right? And the Q hat would be, fairly enough, the
Opposite.
percentage of failures, or the probability of failure. Are you with me? Okay. Percentage, probability, they pretty much mean the same thing, as long as the percentage is a part of a whole. So what does that do? So let's look at kind of problem we could have. So remind me, if I have a problem with, I take N people, and I get P and Q, it doesn't matter if they're wearing hats or not. First question I want to ask is, what's the mean of that situation? Good. So mu is NP, so NP hat somehow is like X bar. Does that make sense? If P is population, NP is the population mean. NP hat must be the sample mean in a way. You guys kind of with me?
Yep.
Okay. How important is that little bit? Not really. It's just to make sure you see why things are in the right place. What's the standard deviation?
NPQ. Population.
Good. So what's the standard deviation for the sample?
NP hat and hat Q.
I like it. Cool. All right, so far so good. I just want to make sure you understand where the parts are coming from for this. So now what we do is we look, and this is why it only makes sense to me to do 7.3 first. If I look at 7.3's formula, and actually let's be careful, because 7.3's got a, now I understand. There's something we don't want to do. Look back at this formula here. I try to stay away from talking directly about this, but there were a couple people who made this mistake. What were the two triggers that tell me when to divide by square root of n? Change the standard deviation? When I take a sample, and I'm talking about the sample Mean. So in this problem, in 7.2, we're talking about percentages. We're not talking about means. And in fact, for binomial problems, we're not talking about sample means ever anyway. So you never have to do both adjustments. So remember, there was the divide the standard deviation by the square root of n. And what was the other adjustment? Go up or down by 0.5. You never have to do both at once. So what does that really boil down to? The mean I'm going to replace with NP hat. Right? And I'm doing the same thing I did when we talked about, remember I replaced that with x bar? Back when we talked about 7.3, the z came down, and this became sigma over square root of n. Right? That's where we got that formula from. So here, the mean is replaced with NP hat. Z score comes down. Standard deviation is replaced with
standard deviation divided by
NP hat Q hat. How are we doing so far? Is that good? Decent? Live with it? Does it make some sense? Okay, hopefully. All right. So let me take this out of the way. Now this is still not good because it's still not talking directly about just percentages. Because will this be a percentage? No, it's going to be a number, right? N times percentage would be a number of people that are left-handed or whatever. So what I effectively want to do, and just in case any of you are worried like you should be, I'm trying to approximate this. I take a sample percentage, I take a sample of people, and I get a percentage that smoke. But I'm trying to approximate the average number of people at Grossmont that smoke. That would be the parameter. That would be N times the population percentage. Let me just stop right there, let that all sink in. So I'm trying to use this to approximate this. But I don't want to talk about numbers of stuff. I want to talk about percentages directly. I want to say it's 28%, give or take 3% or something. You with me? I want to talk about pure percentages. I want to get rid of what then? What do I not want there? I want the percentage by itself. So I don't want
Sample percentage?
I don't want n. Right? So if I divide by n, now I'm approximating the percentage itself. It's going to be a lot more like Gallup had. The percentage, not the average number of people who don't know. I want the percentage of people who do something. So that would be, now that's p hat, give or take. Now help me out here. Who's good enough with the mathematics that actually knows how to do something? Can the ends cancel? Good. All right, thank God. All right, good. They don't have the same root, so they can't cancel. So what could I do with n to make it have a square root on it? What's n the same as? The square root of n squared. I love it. So now if I just do that, I didn't change anything. I just put more symbols down there. It means the same damn thing, right? So how many n's would cancel now that they have the same root? 1. So now the formula is p hat q hat over n. You guys kind of follow where that came from. These are formulas that we knew before. Formulas we knew before. We threw a hat on some of them just to make things festive. And then we divided by n just to get rid of it, just to talk about percentages only. So you can see how it's coming from old known stuff. We added the idea of the hat to go along with like the mu x bar distinction, population sample. So now we got population no hat sample hat, right? And then we stripped off the end to get to that. That's the formula you're going to use for 7.2. And then the work is very much like 7.3. They're going to have to tell you these things. You're going to look up that based on how confident you want to be, so forth, right? 7.2's work is a lot like 7.3's work. The weird thing is the problems are going to be a lot shorter. They don't have to tell you as much. They really only have to tell you p hat. Because then what's q hat going to be?
Same thing.
The rest. Right? So it's almost going to feel like they're not telling you enough to go off of. So let's try a problem together. And then I got a really freaky handout for this one. I can't remember the number, but oh well. All right, we've talked to 738 Afghans and find 493 of them have no confidence in the. It's unfortunate that word came up, but oh well. They have no confidence in the elections. They don't trust the elections. The word confidence is, of course, different.